Friday 13th. So. Welcome to the lectures. Okay, so today we will continue with Faddeev-Popov quantization. So today I will talk about Faddeev-Popov ghosts. So first, let me recall last lecture. So we ended up with the theorem which says that the integral over m under the conditions that we spelled out last time is equal to h to the power, which will be determined soon. So it's equal to the integral over the supermanifold, where the even part is the Cartesian product of m cross g, and the odd part is g cross g star. Coordinates on this manifold are x lambda cc bar, lambda, and then dx, dc, dc bar, d lambda. So I defined last time what is the supermanifold, and here it's h to the minus n. The Faddeev-Popov action, and I'm saying Faddeev-Popov action having in mind that eventually function f will be the action of our field theory, and this will be the formula for the path integral. So it's equal to f of x plus sum over a from 1 to n, lambda a minus ih, sum over np from 1 to n, c l a b. Now I have to careful about upper and lower indices, so it's CRA, CB. Now, the assumption is that M is a compact manifold, so we don't have any, so that we would have no problems with the convergence of the integral. dx is the volume form. There is a Lie group acting on M. So that f and dx are in the M. Functions phi.
Any conditions on the action?
What?
Any conditions or assumptions on the action?
The assumption is the following. Critical points. Yes, so the action is with no stabilizers. Or to be more precise, the statement is the following. So the condition is the following. Well, the condition that we will need for the next step. So this is a very strong condition that realistically is not happening if G is compact, acting on compact manifold.
I mean, if that was the condition, just go to the quotient and refer to the previous discussion.
Yes.
Right.
So there are stabilizers. So, but what we will really need is the following: critical points of f form finitely many G orbits, and there are no stabilizers on each of these orbits. So it's important where critical points of f are for the Cauchy asymptotical formula. So okay, so this is the, and basically I proved that this formula follows from the identity where you can write this integral as the integral e to the I f of x, the determinant of the matrix L, and the delta function supported at the level 0 set of functions f dx, and I didn't remind what LAB is, so I assume that we choose the basis E sub A in the Lie algebra G. So then S phi, the zero level of these functions, is a cross section through G orbits. And again, realistically speaking, when you have a compact manifold and compact Lie group acting, there will be orbits with stabilizers. So this formula holds in case when these orbits, I mean, there is a measure 0 of these orbits. So the assumption is that this is a cross section through G orbits, and again, I will put here the word generic, meaning that it's not going to be a perfect cross section. It's not going to be something that parameterizes the quotient space, because quotient space is not very good space. So, but generically, it's a cross section. And what's really important for the future is that and that's the only thing that will be important for the asymptotical formula, asymptotical expansion of this integral, is that it's a cross section through orbits. Let me call these critical points formed. I'll call them critical orbits. So SP should be a cross section through critical orbits, or rather through the vicinity of this critical orbits.
So it should be just transversal to a critical orbit.
Yes, that's transversal critical orbits.
And I guess it doesn't matter how wild the action is away from the critical orbits.
No, absolutely. For the asymptotical expansion, it's not important.
So first you localize the integral, and after that you reformulate it in terms of slice and so on.
Yeah. Okay, so I think now I recall all the setup. So last time I demonstrated it's rather obvious. So you simply write the determinant as the Grassmann integral, and you write the delta function using the Fourier transform with respect to lambda, and you get this formula from this one. So now the question is how to prove this identity. And I forgot to put the volume of G set here. And maybe since it's there, it should also be over here. That's important, because if the situation is non-compact, if we have a function here, say, which is rapidly decaying, and if it's also G in the end, then we may as well consider the case when G has an infinite volume. But then this integral, of course, is completely meaningless. But we can sort of, instead of considering this integral, we can consider the integral here, which represents the integral over the space of cosets. And the space of cosets may be compact. So that's sort of the idea of this approach to quantization of gauge fields, that in gauge theory, the volume of the gauge group is infinite. So this integral is completely meaningless. But the integral over the cosets, which is represented by this integral, makes sense. So at least theoretically, that's the conjecture. Okay, so let's derive this formula under all our assumptions. So basically, I will follow to this Fadeev-Popov trick. So step number one is, so let's find the Jacobian from this identity. So there is something remarkable about some statements. You know them by heart, but then every time you try to reproduce them, you have to look at notes. So to me, this statement is of the same nature. So
what's delta of x?
delta of x is simply the Jacobian. I'm going to compute it in a second.
Jacobian of what?
Of the transition, yeah, you have the coset, you have the volume measure here, you have the volume measure on the group, and so it's the essentially it's the formula for the it's how to compute the volume form on the space of cosets. It's roughly speaking like this.
So delta x is that quotient.
Yeah. That's how you can think of it.
Can you just write that this is equal to delta of x?
I don't want to do it. so let's just look at this.
But so this is really a question of the measure of the Dirac distribution.
Yes, exactly. So when you write yeah, suppose it's I can say this. So h dx dg, right? So, but then we have the correspondence between this slice, between this cross-section S and the coset, which is at generic point is an isomorphism, but this one has many singular points which may be missed by this cross-section.
We don't care about that
We
because
don't
all
care
we
about
need
that,
to
so-
do is an analysis of each of the critical orbits where everything is a smooth action.
Yes. So
With no
so
self-resistance.
this is some map from M cross G to a cross section, and and this delta is the Jacobian between this measure and the induced measure on S. Okay, so let me compute this delta. So let's assume that and I forgot how to prove this theorem, so let me just look at my notes. Yes, okay. Okay, so here's the idea. So we insert, that's the trick. So we take this integral, f of h, we insert this identity here, and then we change the order of integration. So it's f of x h del x delta gx dx. I didn't sleep well enough with this. Well, let's just try to figure out together how to do it. So this is so we want to write the integral you have a conjecture on it. No?
Well, like you do.
Okay.
How much do you think could we choose x equals gy?
That's certainly a good idea. I'm absolutely confused. I will tell you why I'm absolutely confused. I'm absolutely confused where to get this delta function of phi of x. And
Well, I mean, that's because of the group invariance. I mean, right? Locally, the space will be G cross S.
yes, that's right.
And now we have some measure on G cross S, which we want to reduce down to now an integration over S.
It's even G phi is mapped from X to G, the algebra.
Right.
It's even G
Yes,
algebra.
we can do it this
cross
way.
X.
Yes, sure.
Yes.
Sure. That's right.
So Hans, why don't you switch the